Welcome everyone to the first presentation of this year's Asia BSDCon. I'm Joerg Sonnenberger, hello. Our topic will be bulk building in the many-core area. So what's on the agenda? I'm first going to give a brief introduction of the bulk building framework of package source, which is pbulk. I'm going to discuss some of the changed requirements we have. I'm going to look at a number of templates for configuration as I would recommend for practical deployment. I'm going to compare the runtime impact of a number of configuration choices. And finally, I'm going to look at what is currently in progress or hopefully soon to be in progress work. So the pbulk framework started out as a project for Google's Summer of Code 10 years ago. The goal was to provide binary packages and regression tests for both the package source infrastructure and individual packages at the same time. This is easily seen reflected in the requirements. So we want to be able to do parallel builds using sandboxes. There are a number of different technologies that can be used for this purpose depending on your operating system. On NetBSD we typically use changeroot. On FreeBSD and Dragonfly you can use changeroot but also jail to get a somewhat stronger isolation. On Solaris derived systems you can use zones, and the list goes on. Most operating systems that can be used in a server deployment also have a mechanism around to isolate builds, even if it wasn't originally intended for that. I strongly wanted to do distributed builds in a local network. The local network requirement is only here because I want to have a low latency and high bandwidth links. In theory, there's nothing here that stops you from running a bulk build distributed over the world. And actually for some of the slow architectures that might be a valid desire anyway. It's very important that we get reproducible build results. So if you want to find bugs, it's very nice if the bug happens the second time when you are actually investigating it. And of course we want to be able to adjust the generic framework for the specific needs of our own environment. The original assumptions of the framework was that it's possible to share certain resources using null mounts or NFS. It must be possible to restart a bulk build when it's been interrupted, for example because your ancient hardware just crashed because, well, it's old, or when you are deploying a current development tree, there might be a kernel bug you are hitting and so on. And it should be possible to have a start and forget mode, so it's kind of important that the build doesn't hang overly long because something is broken. In the 10 years since pbulk was originally written, some of the requirements changed. So when I wanted to use shared file systems 10 years ago, nowadays I'm strongly preferring explicit file transfers and minimizing the use of shared file systems. I'll come back to that later, we'll see why. One of the weaknesses of package source is that figuring out what packages should be built and what the requirements are, like the dependencies, is a very involved process which is quite slow, much slower, for example, than in either FreeBSD or OpenBSD ports. So we want to avoid that as much as possible nowadays. It should be possible to run the master process of a distributed build on a completely different architecture than what you use for the slaves. For example, if you have a local x86 server which is also serving your storage needs, would be very useful to have that as a master node, because it's very likely to also be very stable hardware, and on the other hand have a dozen cheap ARM boards as build slaves, and if they crash, well, they'll stop a single build but not the whole process. It would be nice to have a better semi-interactive use case for developers. So you start a bulk build, you see, oh crap, Python doesn't build anymore. Let's check out how to fix that, and then how do I tell the system, well, try that again, and then continue with the build. We want to have a much better integration of assigning binary packages. We've had support for assigned binary packages for a very, very long time. It was in the use of Alistair, so but it hasn't been integrated very well. Some of those things changed. It's still not where I want to be, so we are working on that. And we also want to improve the build scheduling. For example, if you can build something like 20 or 30 packages at the same time, you'll notice that at the end of a bulk build, you have something like LibreOffice or KOffice, which takes like 5 or 10 hours on its own to build, and it tends to introduce a lot of stale time. So let's look a bit more into the details of how I would recommend you to configure pbulk for bulk building, either for internal use or, for example, for official packages for your operating system. The first critical area is handling the distribution files. I've been using a shared file system for that for a long time, and it comes with some interesting problems. Like if you have two builds of the same package or the same package location, for example, Python modules are typically supported on NetBSD for three or four different Python versions. So the first version starts to build, tries to fetch the distribution file from the internet. The second one starts to build this. Oh, you already got that file. Oh, it has the wrong checksum. Well, let's try to fetch it again. First build has now got everything. Oh, why? Someone overwrote the file, which is still incomplete. Oh well, go away, I failed. That's not very useful. One way to deal with that is use a local mirror, and we have a pretty new hook in the framework in package source to say, well, after you got a dist file, call this shell script with the location on the internet you got it from, and then we can do a bit of very trivial shell magic to decide, well, this is a new file because it wasn't from our local mirror, so let's send it to the local mirror. That can be done using curl, for example, and HTTP post request, or for example SCP. The second shared resource traditionally are the log files, This might be a bit surprising, but when you write standard output and standard error to a file that is on NFS, you'll occasionally get failing builds due to temporary I/O errors. When you use null mounts, you might get some additional log contention from that. I'm not yet clear on how big that problem is. So what we have in place is a push model where basically you are building the package, and at the end, if it failed, there's another hook which can then use, for example, SCP to send all the log files to the server. There's an important option for debugging, which basically tells the framework, well, if the build fails, tar up the complete work directory with all the object files, log messages, and so on, and keep it around. This can require a lot of space, especially if something like WebKit, for example, is failing, which can be 20 gigabyte temporary space, compressed to maybe half of it, but still very annoying. Those tarballs are not uploaded with the rest of the report, so they don't consume permanent space. The third important shared resource are the packages themselves. At the moment, we need access to the the binary package files to determine whether or not the package has to be rebuilt. It could be done over something like HTTP in theory, but doing that from a shell script is very annoying and also quite a bit slow. On the other hand, for when you have created a new binary package, you can use HTTP post or SCP to upload it. And this is actually quite preferable because it allows you, when you want to use signing, to do the signing on a separate machine. And this means the key material you are using for the signature doesn't have to be exposed to anything that's running untrusted third-party code. It would even be possible to store those keys on a HSM or use something like a YubiKey if you want to save money on a server. I'm still working on improving the integration for this and providing something that I can actually redistribute to other people, and which isn't a local hack, but I'm working on that. The last important component are the scratch directories. So these are directories that get constantly rewritten. For the prefix where everything goes, so on NetBSD this is typically user package. For SmartOS and macOS this is normally opt local. You normally need less than 1 gigabyte, but for some very large packages might be up to 5 gigabyte. The directory where you are building typically needs much less than 1 gigabyte, but it can easily be 10 to 20 gigabyte worst case. For example, something like WebKit, especially if you want to do a WebKit build with debug symbols. I wouldn't recommend that for recreational purposes. So if you have enough RAM, you can actually use memory file systems all the time, which is very nice because it doesn't create any wear on your SSDs that you might want to use as backing store. It's also possible to use asynchronous file systems, for example, for ARM single board computers. I typically use icantly from a server with a couple of SSDs inside, and then use a asynchronous FFS on top and have that as a backing store. And there are a number of important settings. The seed wrapper framework has been around for a couple of years now, and we are finally at the point where it's a default for most modern operating systems. So the wrapper framework in package source is responsible for isolation and also some portability fixes. So it basically restricts what a package build is seeing. Like if you have an NPlayer, for example, it will look for 50 different multimedia libraries that might be installed on your system, and the wrapper framework ensures that can only use those libraries it's been explicitly allowed to use. The old wrappers were very fancy shell and org scripts, very large, pure magic, but also quite slow. So going with the newer wrappers is easily 10% faster for a full build. The second option I would recommend is using XZ for compression. The resulting binary package set on average will be something like 40% smaller, even if it's going to spend quite a bit of time on the compression. And it's also important to set certain process limits, for example, to limit the CPU time a single process can compute, because there are a number of things that are known to spin around and waste a lot of CPU time. I'm also using pretty aggressive limits on the address space size. So the single process can't consume all the system resources. And of course, depending on your operating system, you might want to raise default limits for processes, processes per users, total number of open files, and so on. There are two ways to do concurrent build with package source. You can use multiple change roots or whatever sandbox mechanism you have. And you can also use the equivalent of make-j for individual builds. Currently, configuration and install phase are serialized, so they consume a lot of time, and you won't benefit from make jobs for those. On the other hand, you have to be careful about not using too much memory. So overcommitting your CPU doesn't really cost anything. Overcommitting memory too much can significantly slow down your system. So my rule of thumb is to count about 1 GB of memory for the compiler per job, and on average 8 GB of memory for a single build. There are some exceptions on both sides, but this works for the majority of the system. So look at how much memory you have in your system and how many CPU cores you have, and figure out what is a good sweet spot. So we've discussed a couple of different choices, and it would be nice to see what's the impact of those. So this is an ongoing project to investigate. It's quite important to really look at the details of how to create an individual sandbox. I'm also going to look at what is the cost hypervisors are introducing. There are some interesting numbers, and if you have further options for something to investigate, please tell me. So the first thing I wanted to check was when you create a change root, on NetBSD you need a couple of sets. I'm normally going with the kernel because some things check it when they want to use dev kman. We need base, of course, the compiler, etc. Games primarily for fortune, because there are a couple of fortune sets and they get a bit annoyed if the fortune compiler is not available. And there are also a couple of things that depends on MISC and text. If you're using native X11 and not the GSoC from package source, you also need a couple of more packages. In total, it's something like 500 megabyte. If you're using X-source, it's another 100 megabyte. I'm pruning all man pages because those are really not needed for the build. And the first two options I compared were using a read-only memory file system and creating a single image on a fast file system and then using null mounts to duplicate the majority of it. So for all the benchmarks, I'm using NetBSD current. For the majority from July last year, some of the Zen and SmartOS cases also use a somewhat newer NetBSD from November, but that shouldn't be a major factor. The tests are done on a dual CPU Xeon with a total of 16 hardware cores and hyper-threading active. There are 64 GB of RAM and SSDs whenever something is required for local storage. So comparing nullfs and tempfs shows a small difference for the scan phase. The scan phase is primarily running a lot of make instances, but has very little disk I/O going on otherwise. On the other hand, for the full build, we see a significant runtime difference. So using a null-mounted root file system takes almost 30% longer for the bulk build compared to having a single tempfs for every change root. The primary reason for that is there's a very high lock contention on the vnode for the root of each change root. Some of them, I suppose, is due to the aggressive change root escape checks NetBSD has, which are much stronger than any other operating system. But it could also be a couple of issues in the locking protocol when nullfs is involved. So for all later tests, I'm actually going with a single tempfs instance and forget that null mounting is an option. The second important test case I wanted to see was what Zen is introducing in terms of overhead. Because this is actually what we are doing for the official bulk builds on TNF hardware. So it's the same basic setup. The Zen case is using a pretty small NetBSD .0 and 15 GB RAM per DOM-U for the for the multi-guest case and a single 60 GB DOM-U for the single case. So the scan phase for the single DOM-U case was kind of expected because the system call overhead was then is quite a bit higher. And also the slowdown for the full build was within expected parameters. I did a couple of tests like this 10 years ago using other virtualization technologies, so this wasn't really a surprise. What was a surprise was when I went from a single DOM-U to using 4 different DOM-Us, because now the scan took 1/3 of the time. Virtualization made things 3 times as fast. Okay, and for the scan phase, for the total build, it was still about 10% faster. What happened? So when you watch the scan, especially the scan phase on this 16x2 core box, you'll notice extremely high log contention in the NetBSD memory subsystem for the free page queues. So the free page queues are protected by 2 different global logs. One is a spin log, one is a adaptive mutex, and this is not working very well when you have a very high spawn rate for processes. We even have a global free list and a per CPU free list, but still have only a single log to protect that. So this is kind of silly, and we really have to fix this because it's embarrassing actually. But the hope is to actually see the bare metal numbers going down at least as far as the Zen PV numbers we see right now, and I expect we can actually do quite a bit better, because when you look at the single DOM-U case, it kind of shows what overhead we normally see already. So it should be possible to get the scan phase on this hardware hopefully down into the 25-minute range.
I have a question. Could tell me the number of cores for the bare metal machine and for each DOM-U?
Okay, so the question is, what are the number of cores? So this is a system with 16 physical cores and hyperthreading, so a total of 32 virtual CPUs. For the bare metal case, I'm expecting the system scheduler to handle that, so there's no thread pinning or anything involved. For the single DOM-U case, I'm assigning 31 virtual CPUs to a single DOM-U, and kind of leaving 1 virtual CPU for the DOM-0. For the 4 DOM-U case, I'm assigning 8 virtual CPUs to the first 3 and 7 virtual CPUs to the last 3, but I'm letting the Zen hypervisor actually do the scheduling. I'm not pinning anything for that. So what I'm trading effectively is a log contention in the memory subsystem for less memory per individual guest. So if you have one of those builds that require a lot of RAM, they might start actually swapping now. Well, before I've never actually had to hit swap for the bare metal case. So the second case I wanted to investigate is what is the impact of full virtualization, because this is what you typically see in cloud deployments. I'm not aware of any cloud provider nowadays that support Xen parallel virtualization mode. It's pretty much dead on the Linux side. No one uses it anymore. So I'm again taking the configuration with 4 different guests and comparing Zen HVM with the KVM found in SmartOS, which is one of the Illumos-based systems, and Joerg also provides cloud services. So for the scan phase, I'm again seeing quite a bit of overhead compared to the fastest mechanism I have, which is PV. This is quite interesting because when I spoke about this with other people, it was always that parallel virtualization is supposed to be actually slower nowadays. So this was a bit of a surprise. And for the full builds, HVM is much slower again than the bare metal configuration. There are some timing differences between HVM and KVM here. I'm attributing that to better device drivers when using KVM, because NetBSD currently doesn't use virtualized drivers under Zen when running as HVM guest, which again is a bit of a bug, but for KVM we are using Virtualization drivers, which are somewhat more efficient. So from all those benchmarks, what do I want to change on the package source side? Well, there's still the question of where the up-to-date check for a package should be. Doing it on the client has a requirement of shared file system for packages. Doing it in the master would make it much easier to sidestep that, because the master often also serves the package directory. It brings a number of protocol changes in, and I'm not completely sure yet how to deal with that. I'm going to move the data storage in the build process into a SQLite database. It's currently using a lot of text files, reading them in as it starts up, and with the addition of actual dependency data for fast rescanning, it now requires something like 100 megabytes for the master process, which is a problem on older hardware. This would also make it easier to move to checksum-based up-to-date checks as opposed to time-based checks like I'm doing right now. I want to integrate my idle process monitor. I've had this one around for a couple of years. It uses KQ to monitor a process hierarchy, and if there's no fork, no exec, and no process getting terminating for a while, something is likely going wrong. Two pretty infamous problems are Onyx, which is some strange language implementation, and, well, the last version of GNU-Make. The last version of GNU-Make has some pretty horrible bugs in its job server, and it will just hang around, stopping to collect its zombie children. And yeah, it's nice to have a tool in the infrastructure to catch this. And of course, the last number is for better scheduling. I want to have an estimate of the resource consumption of a build, and getting good numbers for that is actually surprisingly difficult. How long does this take? Like, the wall time is not a good estimate when you have between 1 and 8 different builds on the same machine that can use all the CPU resources or nothing at all. So I'm still working on that. And for the near future, I want to move to a new communication protocol based on HTTP, simply because it makes it easier to also provide monitoring and live feedback, and integrate things like package uploads and log uploads. And of course use the resource data I just talked about to do better scheduling. So that's it from my side. Do you still have questions for me?
Yeah. Please tell me the reason why you choose the HTTP for the next communication protocol base.
Okay, so the question is, why do I want to go with HTTP? Primarily, I can use it as a connectionless protocol. So the system already works as a pull-oriented model from the build slave perspective. So the slave asks the master, okay, I have nothing to do, give me a job. So HTTP fits that very well. The other thing is it's a standard protocol, so it's pretty easy to get implementation of both the client and the server side, which avoids having to support your own involved communication protocol. And finally, if you want to do progress reports, everyone has this fancy devices that can show HTTP servers and do requests to them. So it just avoids having to introduce a second protocol just for status reports. So. Other questions?
States on building on bare metal machines. You said you use a 32-core processor. How many cores work at the same time on the bare metal?
So the question is, what is hardware utilization on the bare metal effectively? Most of the time, around 40 to 50% is spent in userland according to top or other reporting tools. But if you have, for example, a build of Qt and some other big C++ programs going on at the same time, for example, it can easily go up to 80 or 90%. So the overhead in the memory subsystem is definitely the biggest single wasted resource, and fixing that has a high impact. It would be nice to run the same kind of benchmark ones, for example, with FreeBSD. I just haven't had the time, and I mean, one cycle typically takes something like 1.5 days, and doing it like at least 3 times to get some stable numbers sums up. And I actually use this machine for package source development, so keeping it on the same data point to get reproducible numbers ensures that lots of people are breaking things in package source current and won't get slapped for it.
I think package source is for the class architecture and operating system makers, but you are talking about only on MD64 or not?
Okay, so the question is, NetBSD is targeting many architectures and many operating systems. Why I'm talking only about NetBSD? Well, to a degree, because that's what I care about most. And it's a lot of work to use different hardware or different operating systems. I actually expect quite a few things to apply to other operating systems, depending on their specific scalability impact. But I do want to run more numbers for ARM at some point. I just haven't had the time. Other hardware is mostly constrained by the availability to me. So I do have enough resources for ARM and x86 to do a build in a decent time. I don't have any other hardware architecture in my own lab that can do a bulk build in, let's say, less than a week. Okay, the question is whether I talked with Jonathan about doing similar things on Illumos or SmartOS. No, I haven't. We've been talking about a number of things for his deployments on the Joerg cloud, but nothing more precise than that. Okay, in that case, thank you for your attention.